Last time we started with section 6.1. We were talking about rational numbers, and we talked about the fact that rational numbers are numbers that can be written in fraction form, right? So, and the fractional numerator and the denominator as integers. So any number that you can write with an integer numerator and integer denominator is considered a rational number. All right, so you're going to have to tell me where we got to. We're getting close. Is that the one? Fabulous. Okay, equality of fractions. So two fractions, a over b and c over d, are equal if and only if AD is equal to BC. And there's a name that you know that this is called. What is this called when this is happening? How do you cross multiplication? Good. So the way we would get from here to here is usually people think of cross multiplying across the equal signs. So we end up with AD is equal to BC. So if in fact the two are equal, then their original fractions were equal to begin with. Okay, so we are going to determine if these two fractions are equal. There's at least 4 different ways to show whether these are equal. The first one we'll do is exactly on the last slide. So we're going to cross multiply to see this one, okay? So the first one would be what we would have referred to back over there as Theorem 6.2. So let's see when we look at Theorem 6.2 if this actually ends up with the equal fractions. So I have 3 over negative 12. And this is sort of like questioning, is it equal to? We don't know that they're equal, right? It's a question mark. Negative 36 over 144. Now, if you would like, you can ignore the negatives. Why? Yeah, they're both negative, right? They both have the same sign to begin with. So the signs themselves are really not important. And it'd probably be easier if we just would eliminate them to begin with. Is that okay with everyone? They already match. So let's multiply across and see what happens. So grab a calculator for me. We're going to do 3 times 144. Thank you. What is 3 times 144? Can you get it? 432. Okay. And what is 12 times 36? Same thing, 432. So these are in fact equal, right? So the original fractions were in fact equal as well. So this is one way to do it. If the numbers are quite large, maybe you don't have a calculator with you, or maybe you're just trying to do it really quickly in your head, you may decide that this idea of cross multiplying is not super friendly because I don't know about you, but neither of those multiplications that I just asked you to do, if I didn't actually have my calculator there doing it for me, were particularly simple and straightforward to do, right? It's not single digit or even double digit multiplication. There's a triple digit in there. It's not really a convenient problem to do with large multiplication. So let me show you just a few other ways. When you're doing this on your own, it doesn't matter to me what you use, but I just want to give you some options as to how you could do this. So one way to do this would be to simplify the fractions. So on the first one, again, we're going to ignore the negatives because they're both negative, those match. I'm not worried about those. I have 3 over 12. So what number goes into both 3 and 12? 3. So I could divide the numerator and the denominator both by 3. And if I do, what will I get? 1/4, exactly. Now let's do the same thing with the other fraction. I have 36 over 144. Now the reality is that 144 divides by 36. But until I just said that out loud, you probably found yourself not knowing if that was a true statement, because those are large numbers. But if you look at those numbers, do you know something that they do both divide by? 2. And maybe you know 4. Those are probably 2 that you might be able to see pretty quickly. Let's go with 4 just because it'll require fewer steps if we use a larger number. But if you go with 2, it's okay. You just will have to multiply or divide however many more times. All right, so what is 36 divided by 4?
It's 9.
It's 9. And what is 144 divided by 4? It's 36. Yeah. When we get to this point, hopefully you look at those numbers and you say, oh, but those are both divisible by 9. So I could continue on one more step. And in fact, you get the same fraction at the end, right? They match. So this would be a second way of doing this. Again, if you don't like it, that's fine. You don't have to use it, but I do want you to know that there's more than one way to do the problem. Let me get you another option. Third option would be common denominators. Now, the easiest way to get common denominators, this is not the smallest denominator, I'm not talking least common denominator, we'll do that in a minute, but the easiest way to get common denominators is to simply multiply the denominators beside each other, or by each other. So when you look at this 3 over 12, you just multiply it on top and bottom by 144, because that's the other denominator. And your 36 over 144, you just multiply the top and the bottom by 12, because it's the other denominator. So what is 12 times 144? Okay, so the denominators match. That was our goal, common denominators. And now I need some multiplications on the top. What's 3 times 144?
432.
And what is 36 times 12?
432.
Right, and again, they match. We're not finding any new results at this point. We're just seeing other ways to do it, right? So the third option, we could get common denominators. Sometimes that's friendly. Fourth option, and again, there's probably others we could consider too, but as long as we're sticking with fractions, these are 4 good ones. We could look at a least common denominator. That's actually pretty simple on this one to see because of what the denominators happen to be. 12 and 144 have something already that you know about them. You know multiplication tables. You know that 12 times 12 is 144, right? Yeah. So it would be easy enough, so to speak, to take the one that's a 12 and simply multiply it by 12 to get the 144 we already have on the other fraction. Does that make sense? This is quicker than the other problem, but mostly because we happen to know that about 12 and 144, not just because it always is quicker. So we have the 144 on bottom, and then what is 3 times 12? 36. And truth be told, of course those match. Option number 4 is probably the fastest on these. You can do all of that. You should be able to do all of that in your head, and pretty quickly. But that's kind of just because of the fractions that you were given. It doesn't mean that it's always the quickest, okay? Any questions on those? Okay, I don't believe there's any questions that tell you you specifically have to use a certain method. So you'll be able to use whatever makes the most sense to you and to the problem you're given. All right, this is a very similar theorem, Theorem 6.3. If we're comparing two fractions again, a over b and c over d, and we cross multiply, they could actually have a less than or a greater than, either way, this one's greater than, symbol between them, and that will stay the same. So again, we're cross multiplying, and you see that the direction of the inequality stays the same. There's one condition that makes this work, and that's that the denominators need to be positive. Okay? So the numerators could be negative, that's okay, but the denominators need to be positive. So if the denominator's negative, simply make it the numerator that's negative, and then you can still use the theorem. Okay? So taking a look at this one then, we're going to arrange these in ascending order. Ascending means what? Going up, right? Ascending on the stairs. We use the word descending far more than ascending. I don't know why, but ascending order. So in order to do that, we need to have some way to compare these three fractions. And we could use part of this, that'll be okay, but we need to compare three fractions and not just two. So it might not be the most convenient way to do it. I have a feeling if you take a look at those denominators, that finding some denominator that they have in common is probably the most straightforward approach on this one. What would be the least common denominator that 25 and 10 would have in common? 20, right? So one of my numbers is already done. I have 13 over 20. So I'm kind of done with this one. I don't need to worry with him. But the other two need a little bit of manipulation. I have 3 over 5. So what would I need to do to get this denominator? What's that? Multiply by 4, right, on the top and bottom. So what does my numerator become? 12. And the denominator? 20. All right, the other one is 7 over 10. What would I need to multiply this one by on top and bottom? 2. So I have 14 over 20. Okay, ascending order, which means I start with the lowest one first. So which one of these is the smallest?
3/5.
Yeah, this one's the smallest. So the original fraction they gave me was actually 3/5, like you just said, so we'll start with it. What would be my next largest?
13.
Yep, this is my second one. So I have 13 over 20, leaving the 7 over 10 as my largest fraction. Okay? If all you give me is this, without some kind of a justification like this, and it may not be exactly like that, maybe you choose a different approach, that's one of those places where there's really no credit to be given because you're not showing how you thought about it. You might have just gotten a lucky guess in there. Probably you didn't. You probably did something, but I need to see what you're doing, okay?
What if we turned it into decimals?
It's a really good question. I'm glad you asked that. As a general statement, there's nothing wrong with decimals, except that we haven't talked about them yet, and your book puts them in chapter 7, which comes after chapter 6. So don't turn them into decimals for now. We'll talk more about decimal ordering in about 3 weeks and go from there. Yeah, but once we've done both of those, like when you get to the final exam, if you did that, that would be appropriate because we would have discussed both. Yeah. Okay, cool. So this one wants us to decide if we are going to put a less than, a greater than, I said it wrong, a greater than, an equal to, or a less than symbol between the two fractions. So again, you have at least 3 approaches as I'm looking at this one, kind of based on when I was looking at these over here, that you could do. 4 approaches. You could cross multiply, that would be fine, but the numbers are kind of big on the problem we're working with. You could try and simplify both of them, that would be okay. You could try to get a common denominator, or you could try to get a least common denominator. And it doesn't necessarily matter to me which one we do, so what would you guys like to do? Common denominator? Okay, so common denominator is usually a good approach when you can look at that and maybe see what they might be able to do. So I think maybe a least common denominator might be a little bit easier here, because I don't know that you really want to multiply 430 by 215, do you? I mean, I know your calculators can do it, that's not my point, but the numbers will get quite large. The larger the number, the more likely you're probably going to make a mistake on somewhere else in the problem. Do you see any special relationship between the two denominators?
3. Wait, no. Never mind. I'm sorry.
They're divisible by 5, that's true. Anything else?
15 is half of 213.
Say that louder for me.
215 is half of 1.
215, the second denominator, is just half of the first one. Do you notice that? So if you happen to notice something like that happen, and it does happen, that's a good place to start. Because what that means we could do on the second fraction is just double the top and bottom, and our comparison can be made very quickly. Not only that, but multiplying by 2 is a very friendly multiplication as opposed to multiplying 430 by 215. So that's a nice approach to this one, but any of the other approaches are perfectly acceptable as well. So what is 51 times 2? 102. And then of course the denominator is 430. So which symbol should I put between them? The less than symbol. Remember, the symbol opens toward the greater number. The number on the right is greater because when the denominators are equal, the numerator on the right is bigger. Okay? So yeah, that would be what we've got. Now I would like you to take a look back at the original problem. Could you see why that has to be true anyway without even getting a common denominator? The second numerator is already bigger and the denominator's smaller. It's a lot bigger, in fact, as we found out once we multiplied it. So it's a reasonable approach to do too. So on this particular problem, you could look at this and actually just argue logistically and saying the second denominator is already bigger with, the second numerator is already larger with a smaller denominator, so the fraction itself must be bigger. You could argue like that, and that would be okay.
Like on the test?
Yeah, sure. Absolutely. What you're doing is you're doing sort of an approximation in your mind, right? That's what you're doing. You're approximating and saying, but I see this sort of a comparison, right? The numerators are not close, the denominators are not close, and they're sort of opposite. And if you don't understand what I'm just heard of describing, that's fine. Don't do it from that perspective. But it is another legitimate approach to do on this problem because it doesn't tell you how you have to decide, all right?
So did we use common denominator or least common?
This is least common denominator. Least common denominator finds the smallest one that they both have in common, whereas common denominator would actually have them multiplied together. And I don't want to multiply 430 and 215, not especially anyway. Yeah. All right, theorem 6.4, 6-4. Denseness property for rational numbers. Given any two different rational numbers, a over b and c over d, there is another rational number between these numbers. Has anyone ever seen, this is an old movie at this point, but has anyone ever seen the movie IQ? You've seen it? Anybody else? It's really cute. It's got Meg Ryan and Tim Robbins?
Yes.
And Tim Robbins in it, and it's got Einstein. It's a love story. It's sweet. You should really rent this movie, or however you would get a movie these days. I don't even know.
I think it might be on Netflix.
It might be on
I've watched it
Netflix.
for a
Go look up IQ. It's really sweet. There's a point in this movie where Meg Ryan, who's very, very brilliant, Tim Robbins is a mechanic, actually, I think. And he falls for Meg. And so, I don't know what their names are in the movie, but whatever. And Meg is Einstein's niece. And he asks her to dance. And she said, that's not possible. And he's like, what are you talking about? She said, because anytime I go from me to you, I cover half the distance. And if I only cover half the distance every time, I never get there. There's that idea present in here. This idea that there's always space in between something. No matter how close it is, there's always some space. So the picture that you're sort of imagining is like you would see on your calculator. If you looked at two digits on your calculator and they were like 1.1 and 1.2, right? They're really, really close together. There's always this ability to sort of zoom in on your calculator where it spreads it apart and you see more space between them. Does that make sense? And there's several ways to find the more space between them. One of them is to find an average. Like, for example, if I did this and I said, oh, I could add them together and divide by 2. That's finding halfway in between. That's one way to find the distance between them. And I realize I just used decimals, and I told you just a moment ago not to use decimals, didn't I? Sorry about that. At any rate, the point still is that you could average the two numbers together. But with fractions, there's even an easier way to do that, and I think that's our next slide. Yep. So a over b and c over d are two fractions. The denseness property says there's something in between them. One of the numbers in between them adds the numerators together, adds the denominators together, and divides them, which is a pretty fancy trick. It's actually a lot easier than averaging. Because think about what would happen if you tried to average fractions. I'd have to add a over b plus c over d and then divide by 2. I'd need common denominators, and then I'd have a fraction inside of a fraction, and that's really messy. But this isn't. It's just addition and division. It's pretty clean. So if we take a look at an example of that, we have 33 over 427 and 7 over 92. So according to this theorem, 6/5, what can I do?
33 plus 7 over 427 plus 92.
Exactly. So the top I can see is 40. What's the denominator? What is it? 519. Okay. I'm not sure if there's anything in common to those or not. No, there wouldn't be. So this is it. Yeah, we would have 40 over 519. That number would be between 33 over 427 and 7 over 92. Okay. Very good. Why must there be a number between these fractions? That's a really good way to describe it. I like that. And that's actually arguing again to this denseness property. Right? There has to be something in between it because the numbers are dense. If there weren't a number in between them, they would be equal to one another. So was there a number on that? Yeah, Theorem 6/4. So because the rational numbers are dense. This is not the dense that means dumb, by the way. All right, Theorem 6/4. That's why. They're dense. There's always a number between two numbers, no matter what the numbers are. Okay. 2 examples left, is that right? 8 and 9? Great. All right, we have a student, and they simplified the fraction m plus n over p plus n to m over p. So we have 3 questions we're going to answer. You will notice, if you haven't used our specific textbook before, that there's a section, they have questions on set A, a question set that's called set B, and then a question set that's called connections. I call them set C because A, B, C, and C for connections, okay? So this is a connections type problem. It's supposed to connect the mathematics to the teaching of it, or to the explaining of it, or the theory behind it. Sometimes we'll analyze student work. This would be an example of that. Sometimes we'll give feedback on mistakes that students make. So on this one, the first question is, what did the student do? The second question is, why'd they do that? Why would they think that that's okay? And the third question would be, how would you help the student to see that their work actually didn't work? So we'll start with the student. What did they do? What did the student do on this problem?
Crossed out the ands because they thought they could simplify them.
Okay, so they canceled out the plus n on top and bottom. They did this, right? They did. Okay, everybody good with identifying what they did? Sometimes that's the hardest part of the problem. What in the world did they do to get to there? But as a teacher, you'll have a lot more success at undoing the wrong thinking if you can figure out what they did and figure out why they might have done it. So that's what they did. I agree with you. Why might they believe that this is a valid operation?
Because it's the same number, and we've been taught that, oh, hey, if it's the same number on top and bottom, you can cross that.
Okay,
Would they have known how to cross out with multiplication yet?
they probably would have, but not from the perspective of multiplication, or at least maybe not, but from the perspective of simplifying.
What age range are we talking about?
This would be 5th grade. You're looking at probably maybe later part of 4th grade, but 4th to 5th grade is going to hit fractions. Yeah, so the same number on the top and bottom get canceled, and Brooke is correct. It gets canceled when we do multiplication or simplification, right? So this idea of canceling things is a true fact, but it doesn't work for addition. It only works for multiplication or division of values. So same number on the top and the bottom get canceled when it's simplifying. And I'll say or multiplying. So what might you do to help the students see what's wrong? I mean, like, obviously we can tell them this just doesn't work, but how could you show them something?
You could give
Plug in
the
numbers.
Yeah, I think putting numbers in is a really effective way to do that. So let's say, for instance, that we just have some simple numbers. So let's say you have 5 plus 1 and you have 7 plus 1. Okay? So if you do what the student did, this would be 5 over 7, right? This is what the student's expectation is. But if you simplify 5 plus 1 over 7 plus 1, you actually get 6 over 8. How can I justify that 5 over 7 and 6 over 8 are not the same? Okay, how would you show that they don't equal each other? You could cross multiply. They're small numbers, very small numbers, in fact. So you really could. You could show that 5 over 7 does not equal 6 over 8 by cross multiplying. And this would be a really good example where cross multiplying is fast and easy. So you'd get 40 on one side and you'd get 42 on the other, right? If you don't want to show it that way, you could get a common denominator or least common denominators. You could simplify fractions down into their simplest form. They're almost simplified already. Any of those approaches to show that they're not equal would be appropriate on that. Okay? All right, one more example. If we take the set of numbers equivalent to 1/3 and graph them as points on an xy axis so that the numerator becomes the x coordinate and the denominator becomes the y coordinate, what type of graph do we get? So this is an interesting problem. It kind of mixes a little bit of geometry here in with some number sense. So let's start with the first part of the directions. It says it wants a set of numbers equivalent to 1/3. So we need some numbers that are at least fairly small that are equivalent to 1/3. So let me give you an example. I could also go with -1 over -3, right? That's also 1/3. What's another fraction that's equal to 1/3? 2/6. And let me have at least one more.
3 over 1.
Close. 3/9. Yeah, that'll do it. Okay. And you could have a variety of other things. We could get another negative in here if you want to. We could put -2 over -6. So just a collection of values. Now what it's saying is that it wants all the numerators to be the x coordinates and all the denominators to be the y coordinates. Okay, so basically each of these is turning into an ordered pair. This is the number, 1/3 as an ordered pair. This is -1, -3. This is 2/6. This is 3/9. This is -2, -6, and so on. Okay, so do the directions start to kind of make more sense as I'm piecing them apart? We're going to graph these ordered pairs. Try that again. Okay. So if I have 1/3 on my screen, that's here, and 2/6 would be here, and 3/9 would be here, -1, -3 is here, -2, -6 is here. What type of graph is this creating? It's a linear one. This is a line with one exception. Can anyone tell me if they see the one exception?
0.
Yeah, good job. This point is really not supposed to be in there. Why not? Why is the origin? Yeah. 0, 0 is not on the graph. Because 0 over 0 does not equal 1/3, right? No, it doesn't. It does not equal 1/3. And this is a really good example of one where if you cross multiplied, it actually would equal 0 or equal 0 on both sides. But if you take a look back when we talked about cross multiplication, we very specifically said you can't have denominators of 0 to make this theorem work. Okay, so when we're describing this, what does this create? It says, what type of graph do we get? The answer is that we get a line or a linear graph. It is a line, you wouldn't necessarily have to write this, but it is the linear graph of y equals, let's see, what's the slope? Yeah, y equal mx plus b. The slope is 3, though, right? We rise up 3 and over 1, so the slope is 3. So this is a linear graph of y equals 3x. And it's with a hole at the origin. Or you could say with a hole at 0, 0. Other than that, we get a linear graph.
If we hadn't drawn negative, would it have been fine? Like,
It would, as long as you didn't describe that it's only valid if it's positive. You know what I'm saying? Like if you excluded the negative part as a matter of saying it's not possible, that would be incorrect. But if you still described it as a line where you simply didn't draw it, like in some sense, my graph's not very accurate either, simply because I didn't put arrows on the end, right? And this process does in fact continue, you know, that kind of thing. But you're just trying to give a description of what kinds of a relationship they have. All right.